Hello everybody and welcome to Lecture 2 for the Programming Language Concepts course, CS 311. And today we are actually ahead of schedule, so today we're going to finish going over Chapter 5, which was on names, bindings, type checking, and scope. In fact, I'm going to review a little bit for those of you who missed the lecture because the attendance kind of dropped right before the midterm, and I think it was probably due to the coronavirus, but who knows. So we're going to start in, and I'm going to go over chapter number 5 for you. So this should be a pretty lightweight, easy lecture because most of you have heard some of this stuff already. I just want to finish it up, talk about a few important concepts on it. And then next week on Monday, we will start in with assignment number 5, material, and chapter 6. So yeah, we're very ahead of schedule, so we can afford to be a little relaxed, which is good. So we talked and I skipped the beginning of it when I went over it in class, but we talked about the concept of naming, and naming is the process by which we're going to associate a name with a potentially complicated program fragment. The goal is to hide the complexity, and in programming languages use names for variables, types, classes. Data types have names like int, double, and float. Names provide abstraction. And so, as I mentioned in the in-class lecture when we started this a few weeks back, I said that there are things on the slide set that say design issues, but what I'm really talking about are design characteristics or design features. So what you got to do now is take off the programming hat and stick on the compiler design hat and say, if I were a compiler designer and I was going to design my new programming language and I'm going to use variable names, these are some of the design issues or design considerations that I would have to think about in order to come up with this concept of variable names. And for example, what should the maximum length be? And are connector characters allowed? Are names case sensitive? Are special words or reserve words or keywords allowed? And so underneath the bullet points here for some issues, and these are just a category of just a couple, I should say, in a category of design issues. There are other ones, like what's the scope of the name? Can you reuse the name? Are they, what happens if you're not using the name anymore? Can you get rid of it? There's all sorts of different implementation details to think about. And so on the bottom here where it says length, these are some examples of some variable lengths that we have in different languages. And so you don't have to know, and you don't memorize, like in COBOL there's a maximum of 30, or that Fortran has a maximum of 6, or that there's no limit in C++. You don't have to know this. You don't have to remember this. This is just giving you some examples to put it into perspective so that you're familiar with the concept of names. And, here's some examples. So when it comes to case sensitivity, there's nothing outside of, nothing wrong with it. It's just there's the disadvantage of readability, that names that look alike are different. So in C, C++, Java, the names are case sensitive. So the names in other languages are not case sensitive. So you might be familiar with C++ and Java and C, maybe some Python at this point. Hopefully some Scheme, because you're working on that Scheme assignment. Maybe some Prolog. You might notice that in Prolog, actually, what we just talked about last time, names start out all lowercase, and some of them, there's the case sensitivity changes what the functor name or the parameter names. It has nothing to do with variables because there aren't any variables in that language, but case sensitivity is used to signify different pieces of the language and different components. So we have things called keywords and reserved words. Don't worry about that. This is just some of them, the definitions of the two sort of overlap. A keyword is a word that's special only in certain contexts. The disadvantage of that is poor readability, especially if you don't know the keyword. Reserved words are those that can't be used by the user-defined name. A reserved word would be something like a known construct like switch or case or main. Those are reserved words. So don't worry about keywords and reserved words. It's not really that important either. So when it comes to variables, the variable is an abstraction of a memory cell. I drew this on the board, and we talked about the two components of a variable, if you remember. The two components of the variable is that the variable has a predefined set of values that's associated with it. And so the variable has, like for example, if it's a data type int, there's a number range that the variable can use, and that's tied to the data type. And then there's also a set of operations that are associated with it. And that's because variables in typed languages like C or C++ are defined by the data type. So an integer I has the definition for what I means. And so there's an address that's associated with it as well. So variables can be characterized by a collection of attributes: names, address, value, type, lifetime scope. Not all variables have names. Some of them are nameless. If you look at the Objective-C language, you have ID, that is just a nameless variable. You can have, in C++ or in Java, you can go new something, like new object, and you basically have a nameless object that's out there. The address, you get them with pointers. In other languages like Java, you'll never know the addresses, but the memory addresses is what's associated with where the variable is stored in memory. You might have different addresses at different times during the execution. A variable might have different addresses during different places in the program. And two variable names can be used to access the same memory address, and they call that an alias. In C, C++, the alias is the pointer. We don't have aliases in Java, but we do have reference types, so you can use a reference type to reference something. And I'm sure you guys remember this stuff. We went over it before the midterm. The static and the stack dynamic. And if we go on to the next slide, we see we have explicit heap dynamic and an implicit heap dynamic. I want to review these for you just because I don't have a board to write on, so I have to basically talk you through it. But static variables are the classic C static variables. They're allocated by a stack entry, and they generally are bound to memory before the execution begins, and they remain bound to the same memory cell throughout the execution of the program. They end up in the lower part of the memory. If I were drawing this on the board with the little three sections, with the heap on the top and the stack in the middle and the code data on the bottom, these static variables are on the bottom of the memory there in the code data section. That's the data. And so there's a little bit of lack of flexibility. Static variables don't support recursion because you can fill up the stack entries and you can fill up the static data area. And so you can have a recursive function that runs over and over and over again that causes an out-of-memory error. And then we have the concept of stack dynamic. Stack dynamic uses the heap memory of the process space, and it's a stack, which means it's a runtime stack. It's allocated from a stack entry. In C or C++, and also in Java, we would create a stack entry by saying the word new. So new is a keyword that's on the stack that allocates the memory for us, and the memory ends up in the heap section. So the storage bindings are created for variables when their declaration statements are elaborated. So what does this mean? It allows for recursion because you can allocate and deallocate. The programmer can go new and delete and make, conserve the storage. Some disadvantages is the overhead of the allocation and the deallocation. You actually have to write new and delete to actually manage the memory. And then some programs, they cannot be history sensitive. History sensitivity has to do with if the stack entry created it and it allocated it. When the stack goes away, the memory should also go away. And so a subprogram is like a function. And if a function allocates stack dynamic heap memory, when the function goes away, so does the history of it. We don't know that it's out there. So you could possibly cause a memory leak if you allocate heap memory in a function, but when the function ends, you don't deallocate it. And that's why objects have destructors on them. So when the object goes out of scope, the object itself, using the deconstructor or destructor, however you say it, can deallocate the memory that the object allocated when it was in the subprogram, so we don't cause a memory leak. So There's inefficient references or indirect addressing, which means, the memory's out there, you're using it, but you can't really get at it. It's like through pointers or through references in order to use it. So stack dynamic simply means it's heap memory allocated from a stack entry. And then we have this implicit and this explicit heap dynamic memory. So explicit is something the programmer does. Implicit is something that the compiler does for the programmer. So if you remember that from before the midterm. Explicit heap dynamic memory, as it mentions here, it's new and delete. So you're like, well, what's the difference between explicit heap dynamic memory and stack dynamic memory? In C++, it's the same thing, because C++ is a stack dynamic, explicit heap dynamic. So it's actually both, which means it's always in the heap memory, and an explicit heap dynamic is more specific. It is more in detail. It is more detailed than saying stack dynamic. So it's a little bit more detailed in terms of its description. So allocation and deallocation is explicit, which means the programmer writes the statement that does it. The advantage, it provides dynamic storage memory and management, but it's a little bit inefficient, a little bit unreliable, because if you're relying on the programmer to write something and the programmer writes new and the programmer doesn't delete it with delete, then you're going to cause a memory leak. Or better yet, you did allocate it and then you pointed to it and then another pointer deleted it, and so now you have a dangling pointer. So you have a piece of memory that's missing when it should be there. It's prone to errors. So it is not very reliable. And then I have implicit heap dynamics. So if the programmer's not doing it, then the compiler must be doing it for the programmer. Well, when does the compiler do that? In two cases, the copy constructor and the constructor, the default, or any made constructor in the class. So a constructor automatically allocates if there's a new something written in the constructor. When you make a copy of one object to another object, the copy constructor invokes. And the copy constructor is implicit heap dynamic allocation. So the compiler does it for the programmer, and it does it in certain circumstances when it needs to allocate the memory. Advantage is flexibility. Disadvantage, inefficient, because all attributes are dynamic. And there's a little bit of loss of error detection. Yeah, if you made a mistake in the copy constructor or in the constructor and it fired and it went, and later on, how do you know it really worked? There's a lot, you don't know. There's no error that's going to come back or anything. It's a constructor. You could get something might indicate that it failed or didn't allocate the memory correctly, but then you're just relying on the compiler to do it. So anyway, that was kind of a review. I didn't cover it in too much detail because we actually already covered this in class. We did cover, and we started covering type checking, but I think this is where I stopped actually. So this part is new, so I'll go a little bit slower on it. Type checking. It's what everybody learns when they first learn how to program, because it's the most common error that you get when you write your first program. You put in integer I, and then you have float f, and then you add I and f together, and it says, oop, type compatibility error, type mismatch. So type checking is the activity of ensuring that the operands and the operators are compatible types. So that error came out as a type checking error, because you need to make sure that both types are the same, and you can't add a float and an int together. It has to be two floats or two ints. So then we have compatibility of types, and some languages are called strongly typed, some of them are called weakly typed. The textbook's got a little definition of that. The internet's got a different definition of that. I'll starting with that first so we sort of see what's going on here. The traditional definition of strongly typed languages. So strongly typed languages is a language that type checks everything, that does type checking. And a weakly typed language doesn't do type checking. Might have types, might use types, but there's not type checking. So there's an argument out there on the internet, actually it's a Wikipedia thing, where their definition kind of got changed a little bit, because some idiot confused type checking and strong and weak typing with implicit and explicit typing. And so the confusion there was people said, oh, weak typing is implicit and strong typing is explicit, which is completely wrong, but it's on the internet. And it's been repeated so many times that that's become the new definition. So that's really wrong. It doesn't matter who declares the type. So an explicit type is a type that's declared by a programmer using a keyword like int double float. An implicit type is what we get in Python when we say I is equal to hello world and then I is equal to 5. We can change the type around. The compiler figures out what type something should be, not the programmer. The compiler does it. That's implicit typing. So don't confuse that with strong and weak typing. Strong and weak typing only means if the compiler is doing type checking, it's strong. If the compiler is not doing type checking, it's weak. That's pretty much the definition. So a programming language is strongly typed if type errors are always detected. It's doing type checking. A type error in an application is the operator to an operand of an inappropriate type. A type error is when you're making an operation on two incompatible types. Type compatibility are the types supported by each other, and can the types be used together? So compatibility type is one that is either legal for the operator or is allowed under the language. And the rules to be implicitly converted, or maybe compiler generated code to a logical type. So this automatic conversion, they call it a coercion. So this coercion is when you go like float f is equal to 12. Well, the coercion is going to convert it to 12.000, I think actually out to 6 O's. When the programmer didn't write it in there, they wrote an integer value 12, but the compiler coerced it into a float because the data that the variable is supposed to be typed with is a float. So you get 12.00000 whatever, and that's a coercion. That's an example of what coercion means. Type compatibility means that if I have one variable a and it's storing an integer value 5, and I have another variable b and it's also an integer value and it's storing the value of 15, those two are pretty compatible with each other. In Python, the compatibility is by the structure. So if I have a variable a and it's storing hello, and I have a variable b and it's storing world, I can concatenate A and B together because they're both strings. I don't have to type it, but the compiler knows the type compatibility is that they're both strings. If I get two numbers, then the type compatibility is a number, and if I concatenate or try to concatenate that, it's going to say, I can't do that, wrong type. But if I try to add or subtract them, that'll work just fine. But if I try to add and subtract a string, two strings, I'm going to get an error by the compiler. So just keep that in mind in terms of compatibility. It just means that the types can be worked with each other. So strong typing allows the detection of the misuse of variables that results in type errors. C and C++, and this comes right out of your textbook actually, don't have strong typing because parameter type checking can be avoided and unions are not type checked, and Java is similar. Okay, Java doesn't have unions and Java doesn't have structures, but Java has arrays. And I would say up until about the SDK 5 or 6, maybe 5, arrays were never bound checked. This is the same problem that you have with C++. So in C++, you can create an array, you can call it an integer array, and you can put 10 elements in it. And then when you're using the array, you've declared it with only 10, but you can put like 20 or 30 or 40. You can put as many elements as you want because it's not type checked. So C and C++ don't actually type check everything. Structs aren't type checked, unions aren't type checked. There's a lot of things that don't have type checking. So they say that C and C++ don't have they're not strongly typed language, they're weakly typed languages. And that completely contradicts what you read on the internet that says, oh yeah, C and C++ strongly typed because everything has a type. But that's not really the definition of what strongly typed means. So your textbook is going to tell you that C and C++ are not strongly typed languages. C and C++, however, use what's on the top there. It says type compatibility by name. It means that two variables have compatible types if they are in the same declaration or in the declarations that use the same type name. Int, double, float, those are type names. If I have two ints, they're compatible. If I have two doubles, they're also compatible. If I have an int and a double and I'm trying to add them together, not compatible. So the type compatibility is by name, and the name, not the variable name, but the type name. So if I give it the same type name, it doesn't matter what value I store in that variable, as long as it's the same type name, then they're compatible. So the type compatibility by name is C, C++, Java, anything that uses explicit typing where you give it a name. And I just said in the previous slide, actually, the type compatibility by structure, that's Python. Python doesn't have variable type names, so there's no types. You can convert something to a type, but the type compatibility is by structure, which means that two variables have compatible types if their types have identical structures. What does that mean? The data that it's holding by the variable is the same structure. We have numbers as a generic structure, strings, characters. If the structures of the data, like they're two numbers and I can add them together, then it's supported, they're compatible. So it's more flexible, but harder to implement. The Python typing system is a lot more sophisticated than the C, C++ system is. So, all right, and under the type compatibility by name, it's easy to implement, but highly restrictive. Yeah, if I want to change types to get compatibility, I have a value in a float variable, float f, and it equals 2. I actually have to cast it to an int, even though it holds the value 2, in order to make some operator work with another int. So that compatibility by type is highly restrictive. By name, excuse me. Subranges of integer types are not even compatible with each other. So, for example, on the ints, we have shorts and longs, signs and unsigned data. None of it's compatible with each other. So even though, we have a long and a short, and they're both in the int category, they're all subtypes of ints, we have to cast them to the same if we want to use them the same. So. Scope, that mouthwash you buy at Walgreens, it comes in all those different flavors. Well, not really. Scope is of the variables, the range of statements over which it is visible. So the scope is visibility. Can we see it out of the file? So we have file level scope, we have program level scope. In Java, we have package level scope, we have library scope. We have all sorts of different variations there. In C, C++, we pretty much have static scoping going on everywhere, which means we don't have a global environment. If we want to bring something in, we have to include it in a header file, bring it into the environment. In Java, if you remember, you're importing libraries, but you're not including a half a dozen things. You're just importing the path to the library, which is basically changing the scope. So a non-local variable of a program unit are those that are visible but not declared there. C, C++ doesn't allow you to actually use non-local variables, so you probably have never seen this before. If you've worked with JavaScript and you've done a variable somewhere in the page, you know that you can use it in a function, you can use it anywhere you want. Same thing with Python, actually. Python uses non-local scope as well. I can have a variable that I've defined in the environment, and then I can use it anywhere I want. I can put it in a function and use it. I don't have to redefine it. C doesn't support this, because if I have I outside and I make a function, I have to redeclare I or pass I into the function in order to get it into the non-local scope. So non-local scope is not supported. Instead, you have to pass data back and forth to get the data into the scope. So the scope rules of the language determine how references to names are associated with variables. So pretty much that's a pretty good definition. So static scope is based on the program text. So to connect a name reference to a variable, the compiler must find the declaration. Static scoping is C. C uses static scoping. We put our declarations and then we do our initializations. Well, the declaration is a static scope mechanism. So, the search process, we don't have one because we don't have non-local scope in C or C++. In other languages like Pascal, also in Python, the search process starts with declarations that are local and then increases the enclosing scopes. So let's say we're in a function, so it'll look in the current function to say, hey, if we define this variable, do we know what this variable is? If we can't find it, then we go to an outer function or we start looking for it in other areas of the program. That's a search mechanism. You don't have to know the search process at all, but for languages that support non-local scope, you actually have to come up with a search process in order to resolve what these particular variables actually mean. What values are they storing? So enclosing static scopes to a specific scope are called the static ancestors. The nearest static ancestor is the static parent. Don't worry about that. I'm never going to ask you anything about search processes for scope. Variables can be hidden from units. If you don't support non-local and you only support a local scope, which is what you got in C, C++ allows access to these hidden variables. Yeah, they're not really hidden. We have blocks, a method of creating static scopes inside of the program units. So C uses static scoping. Static scoping is local scoping. Non-local scoping is not static. It's actually dynamic, but they don't call it dynamic. They just say it's non-local. So we all know about the curly brackets, the opening and closing curly brackets. And if I put integer index in here, that's a different one that's outside of it. That's a static scope. Static scopes are supported with blocks. Here's a Java example of static scoping where we have time t is equal to new time, and then we have a system out t, and then t is equal to new time. We can change the time around. The code doesn't really do very much different. It's pretty much the same as the C++ example. It's just showing you Java syntax and changing the variable of a time. This is Pascal code, and it's showing you the nested subroutine rules, where you've got routines inside of routines, and there's static resolution. So there's a search process that searches outside the begins. For the most part, you can skip this. You don't really need to know how Pascal does the searching. So we also have this concept called a referencing environment. And so it kind of overlaps with the concept of scopes and scoping. So the referencing environment is a statement, a collection of all the names that are visible in a statement. Well, okay, so it's the environment for which the statement is visible, aka the scope. So in static scope languages, that's the local variables plus all of the visible variables and all of the enclosing scopes. So that's really the referencing environment. And you're like, what? So the static scope is inside of the reference environment. If you're using static scopes, the accumulation of all the different static scopes, that's the referencing environment, which is just one at a time, really. So you think about referencing environment is another word for static scoped languages using scope. So that's another word for scope. So a subprogram might be active if its execution has begun but is not terminated. That would be the referencing environment. So if we activate a subprograms are functions, by the way. So if we called a function and our scope changed to the function, to a local scope in the function, that's also our referencing environment. So it's a vocabulary word. In a dynamically scoped language, that's one that uses non-local. The referencing environment is the local variables plus everything else that's in active subprograms. Anything that happens to be running concurrently or happens to be open and on the stack is part of the scope. So I'm sure we all have heard of these concepts of named constants. That's a variable that is bound to a value only when it's bound to storage. Doing define at the beginning of the program, setting constant values like pi. Advantages: readability, modifiability. Well, you can't accidentally change a constant variable. It stays. You assign it, you declare it, you assign it a value, and it stays with that value for the life of the program. The binding of the value to the named constant can be either static, called a manifest constant, or it can be dynamic. Don't worry about that either. You're just familiar with named constants that are static because that's how you've done them in C or C++. Java supports it, but it supports it the same way, creates static named constants. Python actually supports dynamic named constants, but I wouldn't worry about learning how to do that one. So we know that we have a variable declaration and we also have a variable initialization. The declaration defines the type, allows for the memory configuration. The initialization binds the value of the variable value at the time that it is bound. So it initializes it with a value. So initialization is also done on the declaration statement. For example, if I said integer I, that's a declaration. I is equal to 5. That's an initialization. If I say integer I is equal to 5 all on one line, that's both a declaration and an initialization. In C or C++, variables are not automatically initialized by default. If I say integer I and then I see out I to the screen, I get garbage. In Java, variables are initialized automatically to a default value. For example, numbers are 0. Pointers or references to objects are null by default. So if I said integer I in Java and I printed out system.out.println I to the screen in Java, what's going to print to the screen is the number 0 because it's initialized already. So Java does an automatic initialization for you for all of the variable data types. C++ never did it. I don't know why they never added it to the language, but if you don't initialize it, you'll either get an error message or you'll get garbage printed to the screen. So control and data abstraction. This is what we get with objects and object orientation, and that's what we're moving into next as a subject matter. In fact, assignment number 5 is on object orientation. Don't try number 5 yet. In the next lecture, spoiler alert, I'm going to give you an easier version for that assignment. So I'm going to give you a better one to do instead. Easier. So for those people who are paying attention to what's going on in the online environment, they're listening to my lectures, or following along, and they're taking the class seriously, you guys will have the benefit of knowing the revised assignment. Everybody else will do the hard one. That assignment is like number 5 if you've looked at it yet. It's extremely hard. It's really ridiculously hard. For 5 points, it's not even worth it. But I'm going to give you an easier version of that assignment, but it's not going to happen until the next lecture because I need to talk about object orientation in the next lecture. So control and data abstraction are two concepts that are associated with object orientation. Control actually, without object orientation, in the regular procedural programming or in structural or imperative style programming, you have control structures. They allow the programmer to hide complicated code behind simple interfaces, classes, routines. But a control structure or control abstraction controls the flow of the program. In an imperative language, a control abstraction would be a loop, recursion, iteration, if, then, else, Boolean equivalent statements, anything that controls the flow of the execution. On the contrary, data abstraction is anything that stores data. So data structures are data abstractions. Variables are data abstractions. Now the object we know has both. It has data abstractions and it has control abstractions. So each object has a list of data members and then it has a list of member functions. The data members are the variables or fields. The member functions are the methods or the messages that are sent back and forth between the objects. So I'm going to have a little bit more on this in the next lecture for Monday, but just know that control and data can be used in and out of object orientation. So binding and binding times. A binding is an association between two things, the name and the object. So if I said integer I, and I used I is bound to the concept that it is an integer type. That's a binding. The binding doesn't do the allocation in memory, it just does the association. It makes it so we've associated it with a concept, and the concept is I have an integer value, and it's called I. That's a binding. Binding times take place at different times during the compilation process. As we've seen back when we were studying the compilation and static compilation process, we see that the binding time could take place at language design time, like when we're designing the language from we're building a new compiler perspective, from language implementation time, when we're putting the pieces together and creating the environment for the programmer to write the code, from program write time, that's when the program actually writes it, to compile time, when they are compiling it, to link, to load, to run. So these are different various times that bindings could occur. Bindings are generally associated with variables, but they could also be abstract concepts. So you can bind a memory address to a method or to a package. That's a binding as well. So bindings are the association between two objects or two things. They create an abstraction of a concept. And just know that the bindings can happen at different times. Now, in statically compiled languages, we have static binding. And you might also, get that dynamic binding occurs with dynamically compiled languages. So let's talk about static first. C static compilation process does static binding, which means everything is done before the program even runs. So the binding is static if it occurs before runtime and remains unchanged throughout the program execution. If I said integer I, and integer I was there, and it was statically bound, and it was set when I compiled it, when the program is running, I isn't going to change. We could do an explicit typecast and change it, but that's going to be set in stone statically as well. So we just don't have any control in the runtime to do anything differently. So C and C++ do C static everything. So it's static binding. Python does dynamic binding. So it occurs during the runtime and change can happen. So I can dynamically bind I to a string if I say I is equal to hello world. And then I can dynamically bind I to an int or a float or a double or something else by giving it a number. And that can change during the runtime because that's when the allocation, that's when the binding is actually occurring, and they call it dynamic binding. Static happens before runtime, dynamic happens at runtime or later or during runtime, and it's changing, can change, it's more flexible. Static is not very flexible. Type bindings, basically if we need to invent the, how are we going to do the type bindings? This is kind of review. We've already seen this already. We have type bindings that happen two ways, explicit and implicit. So type bindings is how is the type going to be specified? When does the binding take place? So explicit declarations in the program used to define for variables. That's when we write the C++ or the C or the Java integer I is explicit, written by the programmer. Implicit declaration is done by the compiler, the first appearance of the variable. Explicit's usually static. Implicit is 99.9% dynamic. When I say usually 99.9, there is an element that could be tweaked, but the majority of all static typing is done static binding is done explicitly. And the majority of dynamic binding is done implicitly. Let the compiler take care of it. So it kind of bridges the midterm, pre-midterm, and the after midterm kind of concepts together. So dynamic type binding is more flexible. Yes, it is. So you have, generic, I is equal to this, I is equal to that. The disadvantages of it is it might be a high cost in terms of calculation. Dynamic type checking and interpretation. I don't know. Type error detection by the compiler is difficult. We don't know what we have in it. So if you just think about, weak typing, What are problems with weak typing? Because that's what dynamic type binding is. It's weak typing because you're not necessarily going to do any error checking. You're certainly not going to do anything statically. Are you going to be able to do it dynamically? And if you do that, at what cost? Are you going to slow the program down by constantly checking it? So type inferencing. There's languages like ML, Haskell. Actually, Scheme would fall in there too. So rather than assigning an assignment statement, using an assignment statement, types are determined from the context of the reference. So we don't assign it a type at all. We just reference the data. Whatever the data is, we infer the type from that. And then we have storage bindings. That's the allocation and the deallocation. So storage, memory. The use of memory in a program is referred to as the storage bindings. The allocation gets the cell from a pool of cells that are available and gives it to the variable. Here's your cell, put your stuff here. Deallocation puts it back into the pool. So the lifetime of the variable is the time during which it is bound to a particular memory cell. When it's no longer bound to the memory cell, then it's died. The lifetime is done. So the lifetime of a variable is generally associated in C or C++. That lifetime is associated with its scope. Because if you have a statically scoped environment that's completely local, variables will go away when the scope changes. And so they will automatically be deallocated and their lifetime will end. So the binding time impact, well, it's crucial impact on programming languages because it could change the way that the memory is being used and the way that the variables are being referenced. In general, early binding is associated with greater efficiency, they say. Late binding is associated with greater flexibility. Late binding meaning Python. Early binding meaning C or C++. It's more efficient to do early binding because, you can check it. You can type check it. It's hard to do that, but you're more flexible if you do late binding. When you say early is static, late is dynamic, by the way. Compiler languages tend to bind names earlier than interpreted languages. Yeah, they do. So that last bullet point here, compiled languages, C, tends to bind names earlier than interpreted languages, Python. So yeah, Python does dynamic binding. So it's doing it at runtime. It's definitely going to be earlier. So in the textbook and sometimes in other literature, you'll see early and late instead of static and dynamic. So early means static, late means dynamic. So the object lifetime, and we're going to get into more of this in the next lecture, is the events in the life of the object, the creation, the destruction. And so the events in the life of the binding, you also have the creation and the destruction. So you have to deallocate the memory somehow, and in doing so, you're going to destroy the binding. So the binding to an object that no longer exists is called a dangling reference. And so some languages get rid of those dangling references completely, and that would be like Java. So if you delete an object and it goes away, the reference is automatically set to null because the binding is removed. And once the binding goes out of scope and it gets removed, then you don't have a dangling reference. Languages like C++ don't do that. You can actually easily create a dangling reference in C++. It's because there's no deactivation or reactivation of the reference. So, all right, storage allocation mechanisms and static allocation. The objects are given an absolute address. It's retained throughout the entire program. This is kind of a review, believe it or not, but it's also giving you different vocabulary. So static allocation, just think static before runtime. The allocation is set before the program even runs. We've got global variables, non-recursive subroutines, and parameters. And then we've got stack-based allocation on a stack, where we have objects that are allocated in a first come, first out, first in, first out data structure, a stack. This would be like a runtime stack. And then we have the allocation structures. For example, here as a calculator, it's just showing you a static allocation structure. So for the purposes of reading this chapter and for the purposes of the knowledge of what you need for the final exam, I'm never going to ask you anything about static allocation. So don't worry about the static allocation. 99.9% of all of the stuff that you've been familiar with so far is static allocation. And it's the allocation of variables that you've done in C or C++. Python and Java both do dynamic allocation. So this is just an example of a stack entry where we've got to read A, read B, sum it together, then write it out. And so we have memory that's holding in the A, B, and the sum. We don't have to worry about it. So don't worry about static allocation, stack-based allocation, or heap-based allocation. If you are curious, it follows through with what I was giving you before with the implicit and the explicit heap dynamic memory. So static allocation actually uses static memory. Stack-based uses static. Heap-based uses explicit and implicit heap dynamic memory allocation, aka new and delete. So, problem with the heap memory, and this is something we're not really going to get into either, but if you take a compiler design course and you start working with heap memory needs to be organized. The code data memory, the static memory, is organized by the stack, and it's automatically cleaned up when the stack entry goes away, but nothing cleans up the heap memory. And so some C++ programmers implement third-party garbage collectors that manage and organize, clean up the heap and free up the memory so that their program has available memory and it doesn't leave garbage behind. So a garbage collector in C++ is not a bad idea if you're using a lot of heap memory. Nobody's going to reinvent the wheel and create their own garbage collector. Instead, what happens is you get a third-party library and you use that to do garbage collection. So you can add garbage collection to C++. You just have to do it through a third-party library. It's not built into the programming language. And so in the Java programming language, they built it in. I said, we're just going to put it in here. So Java does this for you. This is heap-based allocation. So the heap is a region of storage, which the subblocks are allocated and deallocated. This is not the heap data structure. It's a data storage. It's memory storage configuration. And it gets fragmented. And so when you take the operating systems course, you'll learn about main memory fragmentation, and it's the same concept. But this heap space management is used, and this is what Java is actually doing. So this is what Java garbage collection is doing. It's looking for fragmentation, which are holes in the memory. So you have internal fragmentation, which means if the size of the object that needs to be allocated is larger than the size of the available heap, and you don't have enough memory. Or external fragmentation is that the size of the object is allocated is not larger than the size of the available heap, but the available space in the heap is scattered all over the place, and you can't put the chunks together to actually allocate it. So basically, is the space lost inside, and you have, variables and objects taking up more space than they need, and so you have no space available because you've over-allocated. Or do you have empty little bits of pieces of memory all over the place, but you need it contiguously, and you can't allocate enough all in one spot to hold the object. So automatic deallocation after an object has bindings has no bindings anymore is called garbage collection. This is what Java is doing. Java is checking for internal and external fragmentation and is removing the issues of the fragmentation. So, all right. Don't worry about fragmentation and don't worry about garbage collection either, because that's actually not part of what you need to know for the class either. So as I was saying, this concludes chapter 5. I started it before the midterm, but that now I've given you the rest of it. I would definitely read chapter 5. It's not a bad chapter to read. The final exam will focus on 5, 6, 7, and 8. So you want to be reading those chapters if you haven't been doing that. Do not start assignment number 5 yet. You should be working on assignment number 4, which is the prologue assignment, and that's the prologue lecture that I went over on what would have been Monday's lecture. And so the next time I deliver a video for you, it will be on chapter 6. I will also cover assignment number 5 and object orientation as well. I might hit the object orientation before chapter 6, we'll see. So I hope you've enjoyed the video. I hope you're doing well in the class. If you have any questions or problems, do feel free to email me. That's the best way of reaching me. You could text message me if you wanted to as well. I have some students doing that. So hopefully you're all staying safe and you're staying inside and you're not exposing yourself, and we will get through this, and hopefully I will see you all again in person. I don't know if it's going to be before the end of the semester, but we'll see. Anyway, so take care and stay tuned for another video. Thank you for watching.